In this video, I will show you how you can build a really cheap mini-class sumo robot from scratch, using the BBC microbit as the controller. This will be used to control the robot's 2 motors and 7 sensors. In addition to this, we will still have full use of the LED and the 2 buttons on the microbit. The total budget for the build is less than $50. So, since we're building a mini sumo, there are a few rules we have to comply with. First, the weight can't exceed 500 grams, and the size of the robot has to be smaller than 10 by 10 centimeters. There is no height limitation, fortunately. So, we'll start out by sketching out the outline. So, I imagine it will be something like this. So we will need motors in order to be able to move. And we'll also need a couple of wheels. I imagine we'll use an idler for the 3rd wheel, so this will make a stable configuration. We'll need a battery pack. Since the arena floor is black with a white outline, we will need some way to detect if we're close to that or over that the edge of the arena floor. So we'll need to add some optical sensors in the corner of the robot, so we will be able to detect if we cross the arena boundary. And in order to be able to detect our opponent, we will also need some forwards looking sensors. So we could get away with just one, but it would be easier to track the opponent if we have a sensor array in front that can look forwards. We will also need a brain or a controller for our robot. We use the BBC microbit for this. And in addition to this, we will need some magic glue in the form of PCB in order to be able to hook everything up. So sensors will have to be controlled by this, and also the motors, and everything will be controlled by the microbits. Like so. So now we have our sketch, and we can start thinking about which parts we're going to use. It turns out that most of this stuff is readily available from sources like eBay, and it's relatively cheap as well. For motors, I'm planning on using these N20 gear motors. They come in various voltages and with various gear reduction ratios. And this allows us to swap motors in order to play with speed versus torque, etc. If we had a higher budget, we could use something like this. This is a Maxon high precision motor. It's 10 to 20 times more expensive than the N20. So in order to stay on budget, I'll use these. And you can also get toy wheels with snap fit that fits the shaft of these motors. We're going to use the microbit as the controller for this. We need a battery pack. These are for 4 AAA batteries. And for the forward-looking sensors, I'm planning on using these LiDAR sensors that you can get on breakouts, and mount 3 of these in front of the robot. And for edge detection, we'll use optical sensors. These emit a light beam and check the reflection, so you'll get a different signal if you're over a black surface or a white surface. So the only thing we have to think about now is how to connect everything together. So let's start building up our schematics. I'll create a new project in Eagle and then add a new schematic to the project. I'll make one schematic sheet for each functional area. And the first one will contain symbols representing the microbit edge connector, battery, power switch, and also a voltage regulator. Each symbol will have a set of pins, and these pins can be connected to each other by connecting them to the same nets with the same name. And together these symbols and nets will make up the entire schematic for the mini sumo robot. This first symbol is for the microbit edge connector. The microbit will need to be connected to a 3.3 volt power rail and also to ground. In addition to the 3.3 volt and ground pins, I'm going to dedicate P8 and P16 for PWM control of the motors that we're going to use. We're also going to use P19 and P20 since our sensor array and also one other utility chip is going to be connected to the I2C bus. I'm using the net command here in order to draw nets that are connected to these pins. It isn't strictly necessary to change the names of these nets, but it will make life easier for us when we have to deal with multiple schematic sheets later on. This next symbol is for the connections to our battery. Since it would be nice to be able to power the robot on or off without removing the battery, I'm going to use a slide switch between the positive battery terminal and the 6 volt power rail that we will be referencing later on. The negative battery terminal will be connected to ground. The range finding sensors that we are going to use for the front sensor array require approximately 20 milliamps each on average. And since we have 3 of them, this gives us a power budget of approximately 60 milliamps for the front sensors alone. In addition to these, we are going to add 4 optical line sensors, a motor controller, a voltage level translator for the motor controller, and also probably a GPIO expander. This amounts to an average current consumption that probably goes well beyond what we could hope to draw from the 3 volt pin on the microbit if we were to power it via the JST connector. I'm not 100% sure about this, but I believe that the maximum amount of current that you can draw from the 3 volt is about 90 milliamps. So in order to have more flexibility regarding input voltage and also in order to be able to supply more current to the circuit, I'm going to add a voltage regulator. This is a linear version and it's not the most efficient regulator out there, but it requires far fewer passive support components to operate than a switch mode regulator would. It's also big and chunky and easy to solder by hand. We now have both 3.3 volt and 6 volt power available, and we can start working on how to control the 2 motors. For motor control, I'm going to use the L293 chip from ST. This is a 4-channel driver that we can use to control both the speed and the direction of the motors. The next 2 symbols I'm adding represent the N20 motors. Motor 1 connects to outputs 1 and 2, motor 2 connects to outputs 3 and 4. And by applying a logic 1 to the enable 1 pin, the motor will run at full speed. If you apply a logic 0, it will stop. And we can also use a PWM signal so that the motor will see a voltage that depends on the duty cycle of the PWM signal. This enables us to control the speed of the motor as well. Applying a logic 1 to input 1 and a logic 0 to input 2 will make the motor run in one direction, and reversing this logic will make the motor run in the opposite direction. As you can see, I have also added another chip. This is the TXB106 from Texas Instruments. This chip is a 6-channel voltage level translator that will sit between the microbit and the motor controller. And the reason we need this is that the microbit is a 3.3 volt device, and the L293 requires a minimum of 4.5 volts as a reference for its logic pins. Since we don't want to add one more power rail, we will reference the L293 logic voltage to the same rail that we will use to power the motors. The TXP106 has two voltage references. The A side is referenced to the GPIO voltage for the microbit, and the B side is referenced to the GPIO voltage for the L293. Logic signals at 3.3 volt level that are applied to the A1 to A6 inputs will then be translated to 6 volt logic levels on the corresponding B side outputs. The TXP106 has two output modes. It can be disabled by pulling the output enable pin low, or it can be enabled by pulling the output enable pin high. Since we want this chip to be constantly enabled, we pull this pin high by inserting a pull-up resistor between the pin and the 3.3 volt rail. Next, we're going to connect the A1 input on the TXP106 to a net that we have labeled motor 1 PVM. By doing this, we indirectly connect P8 on the microbit with A1 on the TXP106. A2 will be connected to the net labeled motor 2 PVM, which is the same net that the P16 pin on the microbit is connected to. We are also going to define 4 more nets that we will call input 1, 2, 3, and 4. And you may have noticed that we haven't wired up any of the pins on the microbit to these. The reason for doing so is that we don't have enough available GPIO on the microbit to connect these directly. We are instead going to add a GPIO expander a bit later and control these from the microbit via the I2C bus. It's time to add some sensors, so I'll create a new sheet to hold the schematics for these. I mentioned previously that the sumo bot has to be able to figure out if it's about to cross the arena boundary or not. So I'm going to add 4 reflective object sensors that can detect if it is above a reflective white surface or if it's above a dark surface. These will be placed under the robot, one in each corner of the PCB. And the type of sensor I'm going to use is the QRE1113 from On Semiconductor. This consists of an emitter and a sensor, and the emitter emits a light beam and the sensor is a phototransistor. And since there is no current limiting on these, and also because they have to be placed very close to the arena surface, I'm going to mount these together with a couple of resistors on tiny breakout boards. This will make up a module that will be powered from 3.3 volt, and the output will be a logic high or a logic low signal that can be interpreted by the BBC microbit. I'm going to name these signals northwest, northeast, southwest, and southeast. Next, I'm going to add the sensors that will make up our front sensor array. A lot of people use ultrasonic ping modules for object detection, but these are much more bulky, so it would be almost impossible to fit more than one of these to the robot. They're also prone to interference from stuff like high frequency noise. So instead I'm going to add 3 VL53L0X laser range finding sensors that can detect targets for up to 2 meters away. The sensors are pretty tiny, so I'm going to rely on using breakout boards that are readily available from sources like eBay or AliExpress. And these modules connect to the I2C bus and run on 3.3 volts. So one thing you have to be aware of when using multiples of these is that they all come with the same default I2C address. Therefore, we will have to hook up the X-shut pin to the microcontroller. We will use this to configure the individual I2C addresses on power up. And since we are going to continuously pull these sensors, we are not going to use the GPIO1 pin, which is typically used for triggering an interrupt when a new measurement is available. In order to control the motors and also be able to read output from the sensors, we would need 13 available GPIO pins on the microbit. And this is a problem since we don't want to sacrifice the use of the buttons or the LED matrix. I mentioned previously that it would be nice to be able to add new functionality to the robot at a later date. And one way of doing this is to add an expansion port, but this would require even more available GPIO. So I'm going to add an IO Expander chip that connects to the I2C bus. This also runs on 3.3 volts and gives us an additional 18 available GPIO pins. And this means that all GPIO from the microbit will be routed via I2C to this chip. The only exception is P8 and P16, which we use for PWM control of the motors. The GPIO expander is the TCA9539 from Texas Instruments. The reset pin on this is active low, so we will pull this high with the pull-up resistor, and we'll do the same with the interrupt pin. Pins A0 and A1 are I2 address select pins. We'll pull these to ground. And we connect P0, P1 and P3 to the X-shut pins on our range finding sensors. P3, 4, 5 and 6 connects to the output from the reflective sensors. And P14, 15, 16 and 17 we'll use to control the direction of the two motors via our motor driver. And the rest of the available pins we are going to route to a GPIO header that will allow us to extend the functionality at a later date. Before moving on to the PCB layout, it's always a good idea to run an ERC check first. This will alert us to any problems in our schematic. And there are usually some false alarms, but in this case I have a few nets that only connects to one pin, and this is a problem. It turns out that I was inconsistent when naming the input 1 to 4 nets that connect the motor controller to the IO Expander. And as you can see, the names used for these in the IO Expander schematic differs slightly from the names used in the motor controller schematic. So I'll just rename them, do a quick second ERC check, and then move on to the PCB layout. After we have finished with drawing the schematic, we can select the Switch to PCB menu item to open up the PCB layout editor. The default outline of the PCB is a rectangle, but this can be changed by drawing a new outline in layer 20, which is the dimension layer. Here I have attempted to recreate a PCB version of my paper sketch from earlier in the video. Each symbol that we have used in the schematic will appear with a corresponding footprint in the PCB layout. And I will try to place the motors and sensors according to my drawing and then fit the remaining electronics where I can find space on the board. The straight wires that we can see represent the nets that we have defined in the schematic. I ended up with a 4-layer board. I could possibly do this as a 2-layer board, but routing will be much easier by adding a ground layer and the power layer. So the top and bottom layers will be used for routing signals, and the first internal layer is a ground layer, and the second internal layer is used for 3.3 volts. Routing is fun, but it is time consuming. This is what I ended up with after several hours. I'll just do a quick DRC check to see if we get any errors, and then we can start generating the CAM files that I will have to upload to the PCB manufacturer. I also made a variant of the schematics where everything is collected on one sheet. Makes it a bit easier to read. If you're curious and want to build one for yourself, you can find all the necessary files by following this link. Okay. It took a couple of weeks, but now I have received 20 beautiful PCBs from China. So now I can start assembling one or two of these, and then we can start programming them. added some test code to the robot, it still doesn't know anything about how to behave in a sumo competition. So we're going to add some behavior, and I'm going to do this by implementing a really simple state machine. We're not going to do this in the blocks language that many of you are familiar with. We're going to do it in C++. Okay, this is a state machine diagram that represents my take on how the robot might behave in a sumo competition. The circles we see on the diagram represent states, and the arrows that goes between them represent state transitions. So a state will have behavior, and it will map to a function or method in our programming language. And the arrows are messages that can trigger a state transition. So you see we have a start state, a scan state, where the robot will try to align to its target. We have a chase state, where the robot accelerates and moves towards the target. And we have a reverse state, in case it crosses the arena boundary. Then it will reverse and go back to the scan state. So when we boot the robot, it will be in the start state and immediately transition to the scan state. If the sensor is closest to the target, it will enter the chase state. Or if the left or right sensor is closer, it will align and then enter the chase state when the center sensor is closest to the target. So that's it. It's not very advanced, but we'll give it a spin, see how it goes. Okay, I'm not going to go through every detail regarding the implementation on how I interact with the LED matrix or the sensors, but this is the representation of the state machine that we saw in the drawing. The state machine has objects available that will enable it to interact with the display or the proximity sensors in front, or the line sensors, or the motor. So these are the messages that can be sent back and forth in the state machine. And each state has a handler function. So this is the handler for the start state, and this is the handler for the scan state. So in the start state, it will just wait for 2 seconds and then return a scan message. This will cause it to enter the scan state. Here it will reduce or set a relatively slow speed setting for the motors, and then it will tell the motors to just make the robot turn right. So it will rotate on its axis. And while it does this, it will continuously update the readings from the front sensors. And if it detects a target, it will return a message indicating which sensor in the front sensor array the target was detected. If it detects a target directly in front of the center sensor, it will enter the chase state. Here it will tell the robot to move forwards, and it will increase the speed of the motors. And then it will enter a loop where it continuously updates both readings from both the front sensor array and the bottom sensor array. If it loses track of the target, it will return a no target message. This will cause it to go into the scan state again. If it kind of misses the target, so it will have to retrack to find it, it will enter a target detect left or target detect right message. This will cause it to align right or align left. If the robot crosses the white line at the arena boundary, it will enter a reverse state. So it will reverse the direction of the motors and just wait 400 milliseconds and hopefully be somewhere closer to the center of the arena, and then it will return a scan message, which will cause it to enter the scan state again. So it's pretty simple stuff. So this is the definition for our entire state machine. We have a state and a message that can cause a transition to another state. Well, since I don't have a full-size mini sumo arena in my basement, I had to try it out on the next best thing, which turned out to be my black couch in the corner here. So I added some white electrical tape to the surface, and just started playing around with the robot. So this is the state machine in action. Well, thanks for watching. So I'm guessing in the next video I'll be talking about something completely different. Maybe something a bit more advanced than the mini sumo. Or something completely different. We'll see. See you next time.